Welcome to Oddly Real. I'm Nem Stefanovic. The core of every atom in the universe, its nucleus, is composed of quarks or antiquarks. Protons and neutrons, which are part of a family of quarks called baryons, are themselves composed of quark triples. There are even particles called mesons that are composed of both a quark and an antiquark together. Quarks are an unusual fundamental particle, since they do not exist in isolation, only in pairs or triples. The families of all quark-based particles are called hadrons. The behavior of quarks is governed by the strong force. This force is short range and only acts over distances on the scale of an atomic nucleus. The strong force is unusual compared to others like the force of gravity or electromagnetism. Unlike those other forces which diminish in strength when particles are separated further in distance, the strong force actually gets stronger when quarks are separated in space. Additionally, it is primarily the strong force that acts in particle accelerator collisions. This force field gains energy when quarks are pulled apart, and that energy, when sufficient, can be converted into a pair production reaction to create matter and antimatter. This is the reverse process of matter-antimatter annihilation reactions, where matter is converted into energy. In this episode, we will study quarks and some of their composite particles, along with the nature of the strong force. Quarks are fundamental particles of matter in our universe, meaning they are not composed of any other smaller particles, and they have no internal structure. The 6 quarks, in order of increasing mass, have interesting names such as up, down, strange, charm, bottom, and top. The quarks are grouped into 3 generations with 2 different charges, plus 2/3 and minus 1/3. The most common quarks in the universe are the up and down quarks. The quarks in generations 2 and 3 are much rarer. These quarks were discovered using particle colliders at very high energies and higher speeds, enough to produce heavier quarks. Quarks are governed by the strong force, which is a force field between the quarks. The strong field is responsible for how quarks organize themselves to build other particles, like protons, neutrons, positive pions, and many others. There are only 3 possible families of quark arrangements, which we call baryons, antibaryons, and mesons. Baryons, which include the familiar protons and neutrons, consist of 3 quarks in a triple. The antibaryon is the antimatter version of this, which consists of 3 antiquarks. Antibaryons are similar to baryons, except they have opposite charge. A meson is a particle made up of 1 quark and 1 antiquark. They are extremely unstable and don't last longer than a few nanoseconds. All of these variations of quark-based particles are called hadrons. All baryons are unstable except for the proton. Baryons will break down into other particles in a chain-like succession of decays down to the proton. The proton is the lightest baryon and hence stable. For example, an isolated neutron particle will last no longer than 15 minutes on its own before decaying into a proton, electron, and antineutrino. The neutron has slightly more mass than the proton, since the down quark has slightly more mass than the up quark. This is responsible for its instability. It is extremely difficult to measure the mass of a quark, since they do not exist in isolation. Furthermore, the strong force is so powerful that a significant portion of the mass of a particle is part of the strong force itself, or the interaction energies between the quarks. Quarks also possess energy levels within their hadrons, much like electrons can have different energy levels in an atom. However, the energy levels of electrons provide a negligible contribution to the mass of an atom, unlike the energy levels of quarks, which make significant contributions to the particle's mass. In the case of protons and neutrons, they have nearly the same mass, so the quark masses for the up and down quarks are similar. However, the sigma 0 particle and the lambda 0 particle have the same quark composition, up, down, and strange. But the particles have different masses due to different quark energy levels. Greater energies make particles more prone to decay. The strong field is very unusual compared to the gravitational or electromagnetic fields. Quarks fill regions of space around them with a force field, such that other nearby quarks feel an attraction. The field possesses energy. A simplified example of the strong force field is depicted between a quark and antiquark. The field lines are concentrated into a narrow tube called a flux tube. If we try to separate two quarks by pulling them apart, we must use energy. The energy spent to separate the particles is converted into additional field energy, and the flux tube becomes longer. The strong force is only felt by quarks. It is not felt by leptons, such as electrons or neutrino particles. Additionally, the strong force acts over a very short range, only 10 to the power of minus 15 meters, or about the diameter of a proton. In the nucleus of atoms, the strong force is very strong. It is an attractive force that is powerful enough to hold protons together, overwhelming the electric forces of the positive charges that want to break the nucleus apart. It is the strong force that keeps the atomic nucleus stable. The strong force field is different from the electromagnetic field between two charged particles. Both the electromagnetic and gravitational forces lose strength when the particles are separated from each other. They obey the inverse square law, meaning that if the distance between particles is doubled, the strength of the forces is reduced to 1/4. As the particle gets further and further apart, less and less energy is needed to separate them out even more. However, the strong force behaves oppositely to this. When quarks are close to each other, they experience little to no force. As quarks are pulled apart, the strong force grows in strength, becoming stronger with greater distance. It's like an elastic band around the particles that wants to pull back harder the further out it gets stretched. Separating quarks requires more and more energy the further out they are. In fact, attempting to separate one quark out in isolation would require an infinite amount of energy, which is not possible. If the strong force gets stronger with more distance between quarks, then why aren't the quarks throughout the universe producing immense attractive forces across all of space? Why isn't all matter everywhere lumped together into one gigantic quark nucleus? In order to understand this, we need to look at a simplified example of a particle interaction between two protons. Each proton contains quarks. If the two particles come close together with sufficient energy of motion, then a quark might be impacted and pushed away from its triple. If the ejection is strong enough, the kinetic motion of the quark will start to convert its energy into more field energy, elongating the flux tube further and further. If there's enough energy stored in the flux tube, the field energy is converted to materialize a new quark-antiquark pair, causing the field to break. The ejected quark is now part of a materialized meson particle, while the proton has a new substitute quark, possibly changing the particle into something else. This behavior is why the strong force only acts over short distances, since larger quark separations will mean more energy in the strong field, which would break to materialize new quark-antiquark pairs. This is a direct result of the strong force's tendency to increase in strength over distance. This is also why matter across the universe does not feel the effects of the strong force outside of the nucleus. When two hadrons come into close contact, their interaction is primarily governed by the strong force. The force of gravity is too weak to play any kind of significant role in particle interactions. The weak force range is too short, even shorter than the strong force. The strong force would act before the particles were close enough for weak force effects to take hold. The electromagnetic force is a long-range force, which results in repulsion or attraction between particles before the strong force acts. However, if the particles can come together sufficiently close, like in high-speed particle collisions, the strong force will dominate over the electromagnetic force. It is not difficult to produce particle interactions between protons. For example, a beam of accelerated protons can be directed into a tank of liquid hydrogen. The electrons around the hydrogen atoms rarely interact with the proton beam. As such, the hydrogen serves as a reservoir of proton particles. The simplest kind of proton interaction would be an elastic scattering interaction, where the protons simply bounce off each other. If the proton energies are increased, meaning the speed of the incoming protons are made faster, then we will start to see strong force interactions. For example, the interaction of two protons with sufficient energy can produce two protons plus the pi0 particle. We see that we have two sets of protons before and after the collision, but we also have a new particle, pi0, that was created. The experiment is able to materialize a quark and an antiquark pair using the kinetic energy from the high-speed proton. This is the opposite of matter-antimatter annihilation reactions, which convert their masses into energy like gamma radiation. When matter is either created or annihilated, the energy is accounted for according to E equals mc squared. There are rules for pair production reactions, since not just any particles can be created. For example, there is a conservation of charge. It would not be possible to produce an up quark and a down antiquark pair of particles, since the charges are not equal and opposite. Additionally, the number of quarks and antiquarks must be balanced, such that the baryon number is conserved. In another example, we have the following reaction. Proton plus proton can produce proton plus neutron plus a pi plus particle. This reaction materialized a down quark and an anti-down quark particle pair from the strong force. However, the pair did not remain together, but were redistributed across the particles, resulting in the new pi plus particle and changing one proton into a neutron. I hope you enjoyed this episode, and remember, oddly real, really interesting.